tangential acceleration is equal to d omega dt times r. And now I would like to define another item. So we've got a change in angular velocity with respect to time. We saw that when we've got a change in velocity with respect to time, it's an acceleration. So if we've got a change in angular velocity with respect to time, it's an angular acceleration. So here I'm going to define, this is alpha is equal to d omega dt, and this is my angular acceleration. So I can say here that my a sub t is equal to alpha times r. My tangential acceleration is equal to my radial acceleration times my radius. Clock sideways is messing with my head. So, you'll recall that when we're talking about circular motion, we set the zero of our circular motion, or the zero of theta out here to the right. We define our positive direction to be counterclockwise. So counterclockwise is our positive direction of motion. And of course, clockwise would be our negative. Okay, so let's take a look at the diagrams provided here. So if we look at the one on the left, I don't have a meter stick over here. If we look at the one on the left, we see that we've got some initial angular velocity. It's taking our wheel here counterclockwise, so our omega is positive. You know, this is the positive direction of motion. Additionally, we see here that we're speeding up counterclockwise, so our alpha is going to be greater than 0. Our alpha is causing increase in speed counterclockwise, so our omega is going to be greater than 0. Next one, again, we see that we're moving counterclockwise, so our omega is going to be greater than 0. But in this case, we're slowing down. If we're slowing down and our omega is positive, our alpha has got to be negative. This is the same general set of rules we went over when we were talking about linear velocity and linear acceleration. So when we're slowing down, our omega and our alpha have to have different signs. Okay. Next case. Well, in this case, we're rotating clockwise, and we're slowing down as well. If we're rotating clockwise, our omega is going to be less than 0. We're moving in a negative direction. However, we're also slowing down. If we're slowing down and we're moving in the negative direction, our acceleration has to have the opposite sign, so our acceleration is positive in this case, which is what we see. Same thing on the last one. Here we're moving clockwise and we're speeding up clockwise. We're moving clockwise again, and this is the negative direction of motion. So our omega's got to be less than 0. Additionally, we're speeding up, so our omega and our alpha have to have the same sign. So our alpha's got to be less than 0 as well. Familiarize yourself with these, please. Make sure you understand this. said that our position is the derivative with respect to velocity with respect to time. Our acceleration is the derivative of somebody help me out here. No. Our velocity is our derivative with respect to our derivative of position with respect to time. Excuse me. Our acceleration is the derivative of velocity with respect to time. And out of this, we developed a bunch of kinematic equations. And I'll just write down the first two here. Now, likewise, in the case of rotation or circular motion, we said that our omega is equal to the change in theta with respect to time, and our alpha is equal to the change in our angular velocity with respect to time. We can develop the exact same equations as we did for linear kinematics for rotational kinematics. So rotational kinematics is going to give us a set of handy equations that we can use to analyze motion, circular motion. So what's the one thing that I need to add here? The one caveat that I need to make? Yeah, absolutely. Our angular acceleration has to be constant. So our alpha must be constant in order to use these. These equations are developed only and useful only when alpha is constant. So now that I've introduced that idea to you, let's go ahead and do an example. So this is in the chapter problem number 63. Problem 63 says a car starts from rest on a curve with a radius of 120 meters and accelerates at 1 meter per second squared. Through what angle will the car have traveled when the magnitude of its total acceleration is 2 meters per second squared? So this is in the chapter problem number 63. So a car on a curve. The curve has a radius of 120 meters. Our tangential acceleration, it says the car is accelerating, is 1 meter per second squared. It says that the total, it asks, let me put it this way. Through what angle as car travel when total acceleration equals 2.0 meters per second squared. Okay, so we all know the first thing to do here is to draw a picture. My choice on where I put the initial position of the car. So I'm going to put it out here somewhere. I'm interested in the angle that this car has traveled through at some specific point in time, so I'll go ahead and label that. My radius in this case is 120 meters. My car is out there, so I'll just draw a point for my car. See, additionally, it says that my tangential acceleration, a sub t, is equal to 1.0 meters per second squared. And it gives me one other piece of information here. It tells me that my total acceleration, when this thing has traveled through some angle theta, is 2 meters per second squared. How would I draw that on my diagram? Where's the voice coming from? Okay. Okay, and so, how would I draw it?
At the other end of theta.
At the other end of theta up here?
Yeah.
Okay, and what direction? How should that?
Counterclockwise.
Out here, something like this.
Oh.
Okay. Okay. So, specifically, let me address that real quick. But remember that, well, our radial acceleration is going to look something like this, and our tangential acceleration is going to look something like this. So therefore, our total acceleration vector is got to be pointed down in this direction somehow.
Is that acceleration our alpha?
No, that acceleration is A. Yeah. Yeah. So in the problem set statement, it doesn't say anything about angular acceleration. It just says acceleration.
What would be the vector for angular acceleration? So like, which way does angular acceleration go?
Well, let's see. This thing is speeding up, right?
So it just follows the path of the.
Yeah. So if it's speeding up and it's going counterclockwise, we could say that our omega here is greater than 0, and we could also say that our alpha here is greater than 0.
Okay.
Yeah, those aren't items that I included in my particular sketch, but
Yeah.
we can certainly draw those out. You draw too many things and it becomes cluttered and confusing, and yeah, I certainly understand that. So our A here is 2.0 meters per second squared. Now I need to write down something here that I've been negligent on sometimes. Our principle that we're going to use is 2D kinematics dealing with circular motion. Now I'm going to say that we need to recall that the magnitude of our acceleration vector is just the root of a sub our tangential acceleration squared plus our radial acceleration squared. We're told our tangential acceleration. Our tangential acceleration is constant and it's 1 meter per second squared. We're also told the value of A out here in this particular instance in time. We're not told A sub r. It might be useful to find out what A sub r is. A sub r is equal to the root of A squared minus A sub t squared. This is equal to the root of 2 squared minus 1 squared, or is equal to the square root of 3 meters per second squared. And this is the pathway that I chose. There are multiple pathways to work out this problem. And that's certainly something that I've run into as I've been grading your homeworks, is that you guys have all come up with some fantastic different ideas than I had to solve some of the problems. So pretty happy about that. Anyway. So we're given information basically about linear acceleration, and we're asked about theta, so we would like to somehow translate the information that we're given into the language of circular motion. So we remember that our radial acceleration is equal to omega squared times r. Remember we said our radial acceleration is equal to velocity squared divided by r, or our radial acceleration is equal to omega squared times r, or central pedicle acceleration equals omega squared times r. This is one of the equations that I started out the day with as we were discussing that clicker question. Okay, so I can take a look at this one and solve for omega. Omega equals the root of the radial acceleration over r. Okay, well, we've got our radial acceleration, it's root 3. We've got our radius, it's 120 meters. So omega is equal to the root of root 3 over 120 meters. And this ends up being 0.12 radians per second squared. So radians per second. So omega is 0.12 radians per second. So specifically, this omega that we solve for is our omega out here at this point. So we can label that as omega final is equal to 0.2 radians per second. What's that? Okay. So we've got one piece of information in circular motion that's useful here. The other piece of information we can draw from the problem statement. So let me reread this thing. It says a car starts from rest on a curve with radius 120 meters. Well, if it starts from rest over here at this point, that means that our omega initial is equal to 0 radians per second. Let's see. One other thing is we're trying to translate our linear information into circular information. Our tangential acceleration is equal to alpha times r. This is an equation that I developed about 15 minutes ago. So our tangential acceleration is equal to alpha times r. Therefore, alpha, our angular acceleration, is equal to tangential acceleration over r. And in this case, we're given tangential accelerations 1 meter per second squared, and our radius is 120 meters. So our angular acceleration is 0.00833 radians per second squared. Now let's see here. I've got alpha. Alpha is equal to this number here. I've got omega sub f. I've got omega sub I. And I'm looking for theta. So if I take a look at my, my equations, my circular kinematic equations, one of my equations automatically pops out in this situation. The one that looks like this. Because I know my initial omega, I know my final omega, and I know my alpha. So and I'm interested in knowing what my change in theta is, my change in angle is. So solving for my delta theta, this is omega f squared minus omega I squared over 2 alpha. Now we just need to fill in numbers. 0.12 radians per second squared minus 0 squared over 2 times 0.00833 radians per second squared. And we get 0.864 radians for our angle. How much is 0.864 radians? Anybody know? Yeah, me either. It's probably around 45 degrees or so, I'm guessing. So we need to translate this into a value that makes sense intuitively to us. Yep. 49?
49.5.
Yeah, that's a good guess. 45. I wasn't even looking at the answer. Let's come up with that one. So let's translate this thing into degrees. 0.864 radians. And our conversion factor is 180 degrees over pi radians. And this is equal to, well, I'm going to write down 50 degrees because that's what I've got written down in my notes. You said 49.5? Yeah, okay. There was probably some significant bigger stuff going on there. Okay, so there was a lot going on in this problem. The pathway that we need to take when faced with these, when given information in a linear fashion and being asked about a circular value, is just to translate our linear information into circular information. So that really is one of the key steps in these types of problems, translating linear information, or when I say that I mean tangential acceleration, radial acceleration, etc., into angular information. And questions, comments? Just a lot going on. Something's wrong with the edge. Waiting for it to get jammed. That'd be awesome. Somebody up on a ladder in here? That'd be pretty cool, huh? Pretty nice break for class. Okay. So